Rahman Rahim. This is Jahangir Badar Sumro, Assistant Professor, Electrical Engineering Department, Sakkara University. In our first part of the video, we were discussing the paper back-to-back HVDC Modular Multilevel Converter for Transient Voltage Mitigation and Passive Network. In our today's second part, we will cover the remaining portion of the paper. We have already discussed the abstract introduction. We have discussed energy dimensioning and discuss simulation model. The model taken in this case study is a 220 MVA back-to-back HVDC system, and the inverter which is implemented is basically 51 level inverter. Grid is 66 kilovolt. DC reference voltage or DC link voltage is 135 kilovolt. The load system consists of an 110 megawatt passive load and 100 megawatt plus 50 MVA dynamic load. Here aggregate modeling is taken to increase simulation performance, because we already know that detail switch modeling takes a lot of time in simulation, has a lot of computational burden. So for power system studies and for fault studies, aggregate modeling is good enough, and therefore aggregate modeling is selected here. Dual synchronous reference frame, a DSRF, is also implemented in this model. The advantage of dual synchronous reference frame is that even if the grid becomes unbalanced, sorry, so in case of unbalanced grid, both positive sequence component and negative sequence component generates. If the grid is balanced, then there will be only positive sequence component. If grid is unbalanced, there will be both positive and negative sequence components. To eliminate negative sequence component, in case of unbalanced grid, you require a dual synchronous reference frame and DQ0 domain. So DSRF is also implemented in this model. The model is operating in island mode control, meaning that the inverter controls the AC voltage of the passive network, shown in the right hand side of figure 3. Here this inverter operates as an AC voltage control. You see, it operates as an AC voltage control. Okay. And circulating current suppression control is also implemented to eliminate the circulating current. In my previous videos, we have discussed circulating current suppression control in detail, so you can refer to my previous videos. Alright. So this is the model, this is the control implemented in this research work. I have discussed this control, inner loops, outer loops in detail in my previous videos. You can refer to them. Here I will briefly summarize. On the DC, on the rectifier side, there is a DC voltage controller, and there is the AC voltage controller. The output of DC voltage controller will be ID reference. The output of AC voltage controller will be IQ reference. There is also zero sequence controller to eliminate the zero sequence. Zero sequence component will appear in the system when the grid will be unbalanced. So in case of unbalance, there will be positive sequence component, there will be zero sequence component, and there will be negative sequence component. So if there is a zero sequence current, we need to eliminate the zero sequence current by using the zero sequence controller. To transform these currents and voltages into DQ, and then we need to extract the phase angle using PLL. So the input quantities to this inner current control will be the reference voltage of the zero sequence controller V0, the reference output of CCSC circulating current suppression control, where differential voltage will be the input to this inner current controller, ID, IQ, The output quantities of outer loop controller will be input to the inner current control, and this inner current control will give us two quantities Vd and Vq, which will be transformed back to ABC reference, and then we will use a PWM technique here. NLM is used, where from gate pulses will be generated, which will be given to the rectifier station. Similarly, on the inverter side, basically this should not be the DC voltage control. Here's a mistake. This is basically AC voltage control. So this is AC voltage control, and this is reactive power control. So on the inverter side, there is AC voltage control and there is a reactive power control. So so these are the inputs to the inner current control. This is the output of zero sequence current controller, which is fed back as input to current controller. So the remaining portion of the control is same. This portion is same. Only outer control loops are different here. And after inverter, here transformer is used, and then we are meeting the requirement, fulfilling the requirement of the load system. So our objective is that even if there comes a dip on the grid side, it should not affect the load. This MMC, back-to-back MMC, should be sufficient enough to mitigate this dip problem. The missing energy should be compensated by the energy stored in these capacitors, and such that the load should not get any disturbance. All right. Normally, if it is a back-to-back HVD system, its energy will be 60 to 80 kilojoule per MVA. But now, as we are designing a back-to-back HVD system to mitigate the voltage dip issue, so energy will be increased from 60 to 80 kilojoule per MVA to 104 kilojoule per MVA. And with this energy rating, we can successfully mitigate 99% of the voltage dips that were coming into the sun dynamic load passive networks. All right. A back-to-back HVDC system is mitigating a balanced three-phase dip, of which magnitude and duration is as 50% over 75 milliseconds. So there the 50% dip for 75 milliseconds. So how to find dip severity? Multiply this time period with the dip magnitude. You will get dip severity. So dip severity is 0.0375. So this is going to be the dip severity. Delivered power to the passive node network is constant during the voltage dip. So even if there will be 50% dip for 75 milliseconds, it is not going to affect the load power as shown in 5B. You see, here there is a dip. Here there is a dip, and including this dip, this is not going to disturb the power. Power is going to remain constant, 1 per unit to the load. All right. Dip power flow into the rectifier during the dip is reduced. So when there is a dip in the grid, you see this active power flow will be reduced, and there will be a decrease in DC voltage, and it will decrease up to here it is decreasing up to 0.8. Now capacitor should discharge fast enough to ensure that this DC voltage does not go below the 0.8 DC voltage per unit, because if it goes below the 0.8 DC voltage, then inverter has to operate in our modulation region. So we do not recommend to operate inverter in our modulation. So the energy missing, this dip will result into energy missing, and this missing energy will be compensated by the energy stored in capacitors. So during this portion, the capacitors will discharge the energy to mitigate this voltage dip issue. Right. This is a DC power. During the dip oscillation, there comes some oscillation. During the voltage dip, there comes some oscillation in DC power, which can be seen here. So due to the dip, there comes reduction in the active power. If there will be interruption, I mean interruption is the case where DC voltage becomes, where this AC voltage becomes zero. So this dip this dip in the power consumed by rectifier should have been even lower. This might go up to zero in case of when this AC voltage when there come happens AC interruption, AC voltage interruption. But this is a dip, therefore this is not an interruption case, so there is reduction in the active power. So you see voltage in voltage at the rectifier side. Here it is dip 50% dip. It reduces from 1 to 0.5. But this dip does not affect voltages and currents at the inverter side. You see, the currents on inverter side are not disturbed. So voltages are even not disturbed. So this is not going to affect, this dip is not going to affect the inverter output voltage and inverter output current. This is proved from these results. This is another case. This is unbalanced grid issue happening here. So so symmetrical dip. First there was symmetrical dip. This was symmetrical dip. Now we are discussing the case of unsymmetrical dip. So similarly the power is not going to disturb. If there is an unsymmetrical dip on the grid side, this is not going to affect the power. There is some reduction in the power consumed by rectifier, and due to this fault there are coming some oscillation in DC power, but now as compared to previous case DC power oscillations are reduced, and the DC link has also is not also much disturbed. One thing I want to show you, due to unbalanced grid issue dip, there comes by the fundamental frequency harmonic in this DC bus voltage, which we can see here. If you compare this waveform with this one, here we can see that due to this unsymmetrical dip, the second harmonic oscillate, second harmonic order in this DC bus voltage. So this missing energy is compensated by energy stored in the capacitors, and they are going to leave the energy to compensate. They are just going to discharge the energy to compensate this voltage dip, mitigate this voltage dip. Paper proposed that instead of conventional design where 60 to 80 kilojoule per MVA is selected, even this 60 to 80 kilojoule per MVA is good enough to mitigate up to certain voltage dip severity cases. But when you make this design to 104 kilojoule per MVA, then 99% of the voltage dip issues will be mitigated successfully, which were happening in the sun, passive network, dynamic loads. So uh, this paper suggested that back-to-back HVDC MMC is recommended approach to mitigate power, to mitigate the voltage dip issue. But the only issue is that its initial cost is going to be very high. The main drawback of this topology is initial cost is going to be high. In current literature review, recent research work, researchers are preferring to improve the control to such a level that there is no need to go for this increased energy storage. They are trying to make changes in the control to overcome these voltage dip and other issues, which we'll discuss in our coming videos. Thank you very much.